So we saw evidence that when we added up 1, a half, a fourth, we ended up with a sum of 2 from that visualizer. This is a geometric series. So the first term is 1. What's the ratio? Where am I lying to you? Okay. All right. So, do you think that this is always going to work for a geometric series? Because we multiply by half, we got half as big each time our small things added up to something finite.
If the common ratio is smaller than 1. Yeah.
Okay. And so Miko explained what's going to go right if it's smaller than 1, or wrong if it's bigger than 1.
Well, if
R is bigger than 1. If R is bigger than 1, it's going to be bigger than
1. Okay. And wait, so first, hold on. No, because I want to make sure we hear everybody's. So Miko had something to say first. Then
yeah, just if it's less than 1, then there's kind of a limit, kind of like in the rectangles. Didn't go outside of the main rectangle, but just kind of stayed in.
And those rectangles represented the terms, right?
Yeah.
So those are limited. Good. And oh, so you're thinking about negatives. So Amy's claiming if we had, for example, R is negative 1/2, so 1 minus a half plus a fourth minus an eighth, that would still be finite. But if we have, for example, 1 plus 2 plus 4 plus 8, that will be infinite. But she's also saying if we have like a ratio of -2, or we're bouncing back and forth, ladies with us. So Amy's claim is that this also is going to get infinitely big, even though we're adding and then subtracting and then adding and then subtracting. And this will in fact be the case. I'll let you ponder that over lunch, but before you go, I want to equip you with a formula that we can use. And actually, we can just use the formula we had for a finite series and figure out what happens when n gets really big. So for a finite series, we had 2 formulas. Remember, they are basically 2 different ways of writing the same thing. Okay, I'm going to choose the first one to deal with here. So our infinite sum is really just the limit as we increase the number of terms. So I'll call them our infinite sum. Is the limit of these finite sums.
shouldn't it be -1
for the second.
Yes, thank you. Sorry, Shavik. Your classmates are on the ball. Do you think we should continue even when he comes back to talk to the board like it's Shavik? I think we should. Okay, so notice that in this formula, the only place where n shows up is in the r to the n. Okay, but now we said that we need r to be smaller than 1 to make sure that our terms in our series are getting smaller. Like we saw here, so we're adding smaller and smaller things, and our terms aren't getting bigger and bigger, so that's going to give us an infinite sum. Okay, so what's going to happen here? Like if our ratio is a half, what happens is you take 1/2 to bigger and bigger powers, squared, cubed to the 4th to the 5th. It's going to 0? Let's check here. So if you have 1/2, for example, you have a half to the 100th. That's a really small number, right? It's half of a half of a half of a half of a half. It's tiny. So this number As n gets really, really big, the ratio raised to the nth power is getting really, really small. He's approaching 0. Which means that he's gone. So the only thing left on the top is u1 times 1. Well, that's just u1, and that's an eraser. There we go. Oh, it's the first time all year I've done this. And on the bottom, it's still just 1 minus r. So essentially, this term is becoming so tiny, he doesn't matter as n goes to infinity. And here, formula for our sum is just the first term divided by 1 minus r.
And this would be the formula for
But how does that term go to 0?
We're an infinite geometric series.
Okay.
Why is this line 0?
Yeah.
Because we said that our ratio, if we pick a ratio that's less than 1,
Alright, then, yeah.
as we raise it to higher powers, we're going to get something smaller and smaller and smaller.
But if it's more than infinite.
So it only works if our ratio, if the value of our ratio is less than 1. And we'll see that next class as we begin to work some examples with it. But for now, in your last minute of class here, try it with our example that we just did. We said the sum of this series is supposed to be 2. Try, with the first term being 1, the ratio is a half. See if this formula actually agrees with that. And I'll put it in here so you can check.
Yeah, it works.
Section
1 divided by 0.
1
Divided by
divided by
0.5. Because 1 minus a half.
Alright, congratulations! We have just officially moved from the finite to the infinite. Notice that this only works for geometric series, and it only works when our ratio is less than 1. If you aren't convinced of that, I'll show you some tools in the next class that you can use to visualize the graphs of these series.